Thank you very much, Paul. Good afternoon, everyone. So yes, as Paul touched on, MCFP, we're a fairly broad research platform covering lots of different topics. And I think generally looking at the participants we've got here today, I think most of you sort of already would have a bit of an understanding about what MCFP does and the different capabilities that we have. So I won't labor on this too much today, but if you'd like to know more about what it is that we do, please do visit our website here and you'll be able to see all of the different things that we have, the different capabilities that we have. You can connect with us on LinkedIn as well, and you'll sort of see updates and things as we put them up on there to get a bit of a taste of the different things that we do as a research platform. Also on this slide, this is the team as it currently stands. And I guess I'd just like to highlight one thing in particular. I'd like to welcome Raveen to the team and introduce him to everyone today as well. Raveen will be joining us to assist with the Xray characterization node of the platform as well. So you'll get to know his friendly face throughout the next few months with that particular platform if you decide to pursue anything that piques your interest today in today's talk. But otherwise, the rest of us, we each have our own specialties within the platform, all split up here. You can talk to any one of us, of course, and we all each know where our capabilities lie and who best to talk to. So we're a very friendly team. Please reach out to us if you have any questions, and we're happy to forward you to the correct person as well as we go. Okay, so today we are giving an overview of the Xray characterization node of the platform. And this is really just an overview. So we're going to be introducing the two different techniques that we have on the platform, Xray fluorescence and Xray diffraction. Give you a little bit of background information as to what these techniques are, what those techniques will tell you about your samples and how you can apply them together in a complementary fashion. And also we'll touch a little bit on the requirements that are needed for sample preparation for these particular techniques. We won't go into too much detail unless it comes up in the Q&A at the end, of course, about sort of the specifics of how to go about doing this. Please reach out to us and we're happy to chat to you about the specifics of your samples and how to go about applying these techniques into your research as well. But if it comes up in the Q&A at the end, we're happy to chat about that as well. But otherwise, today is really an introduction for the capability and what it can do for you within the MCFP. Okay, so let's actually start talking about these two techniques that I've introduced, Xray fluorescence and Xray diffraction. And let's actually compare and contrast these two techniques here so that you have a base understanding about what it is that we're doing with them. In a very, very general sense, both of these techniques are X-rays in and X-rays out. So if you think about your probe and your signal for these particular techniques, we're putting X-rays into our samples and we're getting X-rays out of our samples. But the interaction that is happening and the interaction that we're detecting is quite different between these two particular techniques. So we've got some schematics here on the screen just to help you to understand a little bit about what's going on. So in Xray fluorescence, we are putting X-rays into a sample. We are exciting that sample. And then when that sample then relaxes down, it releases that energy by emitting another X-ray photon. So that is Xray fluorescence fundamentally. For Xray diffraction, we are diffracting these X-ray waves from the periodic lattice within your sample. So we have X-rays coming in through here. They will constructively interfere if the Bragg condition is met. So when these X-ray light scatters from the periodic array in your crystal, we'll get constructive interference when this 2D sine theta condition is met. And you then get a peak in your pattern, which tells you something about this separation in your atomic spacing. So here we are putting X-rays in and exciting X-ray fluorescence and getting an X-ray photon out. Here we are taking X-rays, scattering those from your sample, and then looking at the angle at which those X-rays scatter away from your sample. XRF then gives you information about the composition of your sample. It tells you the elements that are present in your sample. XRD gives you information on the structure of your sample. It tells you the phases that are present in your sample. So from this, we get elemental identification and quantification for our sample. And here we get phase identification and semi-quantification of the amounts of those phases, or quantitative amounts if you take it a step further as well. In XRF, we can detect fluorescence from anywhere from carbon up to americium, depending on the technique, depending on sample preparation. There's a few things and a few caveats there to think about, but it covers the broad range of the periodic table. And for XRD, diffraction will only really occur for crystalline materials. So we're only going to get sharp diffraction peaks if you actually have crystallinity present. If you have an amorphous sample with no regularity in the periodic structure of the atomic lattice, then we won't get diffraction. You'll just get some amorphous features or just basically a background signal. XRF is generally applicable to solids, powders, and liquids. XRD is generally applicable to solids, powders, and films. And they are complementary to one another. So we can use XRF with our XRD analysis and vice versa as well. So if we now take a look at an example here, so if we had, for example, a white powder like magnesium hydroxide, what XRF is going to tell us about that sample is it will detect magnesium from the magnesium containing phases, but it won't tell us what those phases are. It'll just say there is magnesium present there. It will give us the additional elements that are present as well, so down to some minor and trace level elements present. So in this particular sample, we've got a majority of magnesium present, but we also have calcium, silicon, and small amounts of iron, aluminium, and sodium, for example, present, and we can detect those. But these results, then knowing what elements are present in our sample, can then inform the XRD analysis that we can follow on with. So we can then take this powder sample and we can put it into the XRD and look for the different peaks that we have in our pattern. And from those peaks, we can identify that the magnesium is present in the form of magnesium hydroxide and magnesium oxide. These are two distinct phases present in this pattern here. So the bulk of it is these red lines here for the magnesium hydroxide, but this pink peak here relates to magnesium oxide. We can see some of those other phases as well that we saw from the XRF. So we saw calcium and silicon, for example, in our XRF, but we don't know what they are from. In this case, we can actually identify those as silicon dioxide and calcium carbonate from the XRD. And so we're using the XRF here to basically minimize down the number of search results that we get when we try to do a search match against this pattern. So the XRF is informing the XRD about how to proceed with the analysis. Okay, so let's talk about the two different techniques separately now. We'll start off with XRF because it's the slightly simpler technique to start off with, and then we'll follow on with the XRD after that. So XRF, how does it work? It's relatively straightforward in a sense. Basically, what we're taking is an X-ray tube, a high-powered X-ray tube. In the case of our instrument, it's a silver X-ray tube. We have different filters that we can put in front of that X-ray tube to cut out certain energies if we need to, but otherwise we illuminate a sample here from the backside, from the bottom side of that sample, and we get the X-ray fluorescence coming through to our detector. Now, this geometry or this description of XRF is called energy dispersive XRF or ED-XRF. And it's referring to the fact that we're really looking at the energy nature of the XRF, and we're treating them really as particles and not as waves. And that's how this detector is actually working. It's looking at this discrete energy of all of these X-rays as particles to create the spectrum. There is another technique called wavelength dispersive XRF or WD-XRF, and they are typically higher resolution and can take you down to ppm sorts of detection levels as well, and they're treating X-rays as waves. So they're a different setup, a different geometry, larger instruments, more expensive instruments. This is the simpler technique called energy dispersive XRF. But in both cases, what you're doing, like I said, is you are putting an X-ray photon in, you're exciting actually a photoelectron to emit from the core shell of your atom, And in doing so, you're forcing that atom to then relax, to sort of rearrange itself and kick off an X-ray fluorescence photon. And this particular photon becomes characteristic of the atom from which it came. So we get lots of different energies coming off from the different elements. Depending on how big that element is, tells us how many different X-ray photons we're going to get out, either coming from the K shell, L shell, M shells, for example, but they basically become a fingerprint for the atom that you're looking at. So the peaks that we get from those spectra tell us what elements we have. So the qualitative analysis of XRF is quite simply identifying those elements. So for example, here we have an example XRF spectrum. This is from one of our calibration samples actually, and you can see all of these different peaks that we have in our spectrum. And I've labeled all of these using the software to show us all of the different X-ray lines that we are detecting for the different elements. Now, it's a bit messy, but the software is very good at figuring out which peak is which, and it knows which peak is which. But you can see we can identify, for example, the silicon K alpha line, calcium K alpha, manganese K alpha, this is arsenic K alpha, and then we have these other K beta lines and different extra X-ray energies through here. But this is an example of an XRF spectrum and what it tells you. And you can see that as the elements change, the peaks for those X-ray energies are all in different positions. So these become those fingerprints for your elements. The quantitative analysis aspect of this basically looks at the intensity of these peaks relative to one another. And then it can figure out the concentration of these elements based on the type of oxide that we expect to be present in the sample. We can go from weight percent down to ppm levels with XRF. Now, ppm levels, again, with energy dispersive XRF, it really depends on your sample preparation. It depends on the elements that you're actually talking about. ppm detection maybe is a bit more for wavelength dispersive XRF, but the capability is there depending on how you've prepared your sample and what we're looking for. And the information depth that we get out of this, again, is also very dependent on the elements that we're looking at and your sample and how it's been prepared. But you go anywhere from micron depth to millimeters of information depth. So it's a very, very broad range of information depth depending on what you're looking for and how your sample is being prepared. But the big advantage is it is broadly applicable to lots of different sample types here. So any solid sample, if we can fit it into one of the cups in our XRF, we can probably get a spectrum from it. For powders, we can put loose powders into our instrument inside of little plastic cups suspended by polymer film, or we can create pressed pellets, which allow us to basically run those under vacuum and get much better results from your sample, but that just requires more sample preparation. We can work with liquids as well on this instrument, again, supported by a polymer film, and the choice of that film is dependent on the type of liquid that we're doing, but we can look at aqueous solutions and we can look at oils and diesels actually with this instrument as well. So solids, powders, and liquids we can look at with XRF. A little overview of the instrument itself that we have within the MCFP. So this is a Bruker S2 PUMA XRF, energy dispersive XRF. And this instrument is PC controlled. So often you'll see with these PUMAs that they have a little screen on the front. Ours has actually got a separate computer off to the side to control it and to interact with it. Ours also has the 20 position XY auto changer as well. So here, all of these positions are accessible. So you can mount up to 20 samples at a time inside of this instrument and program it to run through all of that acquisition for you. And this little arm will basically go pick up your sample, drop it down into here, run the sample, pick it up, put it back, and move on to the next sample. And you do all of that programming yourself, and then just let the instrument run through the process. It is a silver X-ray source. It has an automatic filter wheel and vacuum air and helium operation. So we can run powders in air, for example, or in helium as well. Needs to be a really good reason to run with helium, just because it's so expensive to run with helium. But for solid samples and pressed pellets, you're always best to run in vacuum because you will get better results. So as much as possible, we really want to prepare samples so that they can run under vacuum. And just to touch on the different ways that we can mount and work with samples, like I said, we have these plastic sample cups for working with loose powders. And these are basically, they suspend a polymer film at the bottom and you put your powders directly into that polymer film and then into one of these cups in here. And that allows you to look at completely loose powders under air with minimal sample preparation. So that's very fast, very easy. But it limits you to the elements you can actually detect down to. I think it goes down to about potassium, I think is the limitation for running in air. So if you need to go lower than potassium down to sodium, for example, you would want to really press those into a solid pellet. So these are examples of pressed pellets for samples, and this then allows you to run under vacuum, which gives you that light element detection. Similarly to the loose powders, liquids go into these plastic cups as well. And then solid samples can basically be mounted directly into the holder itself. We have a variety of different mask sizes. So this is an 8mm mask, for example. So there's a little hole just here. We have 8mm masks, 28mm and 38mm masks as well for different sized solid samples. Okay, so that's XRF. That's our elemental identification. The next instrument we're going to talk about is, data analysis. So this is the software for the XRF itself called SPECTRA Elements. So it's a graphical user interface here. And basically all of the acquisition and the data analysis is performed inside of the same piece of software. So it has a graphical loader interface, for example, so you can load up your samples, tell it what you want to do on every single sample, and it will automatically run through those for you. The smart oxides and smart elements standardless quantification means that we don't need calibration standards necessarily to look at your results and give you quantification. Basically, we have standards that are running routinely on the instrument all the time to ensure that the quantification that it gives you is accurate, basically. So it's called standardless quantification. And the reporting and the results evaluation is all interactive. You can generate charts, plots, tables directly out of this piece of software. So everything that you need to do is directly on the XRF PC itself. Okay, so let's talk about XRD now, X-ray diffraction. And as we said early on, diffraction occurs when light scatters from a periodic array. So we have here our periodic array of atoms, and we have our incident X-rays coming in and our diffracted X-rays coming out. Now, when the path of these particular diffracted X-rays constructively interfere, that is when they have met what's called the Bragg condition, n lambda equals d sine theta, 2d sine theta. So what we're doing here is we are looking at the diffraction of our peaks as we vary the angle from our X-ray source and our detector together. And this is called Bragg-Brentano geometry, where our X-ray source here and our detector here is moving together. And we get constructive interference. We get a peak in our pattern when this condition is met, n lambda equals 2d sine theta. And so experimentally, we know what lambda is. Lambda is our X-ray source. That is our incident X-ray wavelength. We are varying theta. This is the angles here for our goniometer. So we are systematically varying that. And then we are looking at the intensity of the peaks and calculating this value D from those peak positions. And that D value that we calculate out of your peak positions becomes the fingerprint for the atomic spacing for your particular material, your crystalline material that's under analysis. So that is the XRD technique fundamentally. Qualitatively, out of this, we get an identification of materials. So we take all of those different peaks and we can basically put them into a very large database and say, what does this combination of D spacing match in our database? What materials does that actually match? And that will give you an identification of what it is that you have. So if we look at the example on the right-hand side here, we've got 3 different phases of silicon dioxide. Chemically, they're identical. They are silicon dioxide, SiO2. However, these are three different phases of the same material. So we have quartz, cristobalite, and amorphous glass here. So any one of these will identify roughly what it is. I mean, the amorphous glass is maybe a bit ambiguous to say that that is exactly glass because it is just a large amorphous lump. But you can see that these two phases of silicon dioxide are discrete. They are distinct from one another. And if you had a combination of these three phases in a single pattern, then we can identify that combination of the different peaks present and actually then qualitatively identify them and actually semi-quantitatively identify how much of those are present as well. If we then zoom in onto those peaks, we can actually say things about the microstructure of the material itself. And in particular, one of the common things that we get asked about is crystallite size. So the size of the peak, the width of the peak, will tell you something about the size of your crystal domains in your sample as well. XRD has detection limits down to about 1 to 2% by volume. Again, depending on how well prepared your sample actually is for the instrument and the crystallinity that we're talking about, the actual phases that we're talking about, but it doesn't go down as low as what XRF will do in terms of detection limits. So we're looking about a bottom end of 1 to 2% for powder XRD. Information depth is similar, again, microns to millimeters, depending on the X-rays that we're talking about that are going in and the material that it is, the matrix that it's in, as to how quickly they'll be absorbed actually inside of that sample. We have an example here of all the different sample types that we can put into this instrument. So I won't list them off all here, but again, it's fairly broadly applicable. If you have crystallinity in your sample and we can get it into one of the sample holders that we have, we can probably get a diffraction pattern from it and actually identify hopefully exactly what you've got. This is just an example of salt, for example, sodium chloride. And you can see here that the majority of what we see here is sodium chloride. And we can identify all of the different crystal planes within the material here with these particular stick patterns. So this underneath this, you'll see there's a little black line. You'll see that more easily shortly. That is the actual pattern here. These vertical stick patterns are matches from the database to say this particular pattern matches salt or sodium chloride in the database. And if we zoom in further, right down to the bottom end, we can start to see some of the extra phases that are present. So again, the red lines here are the sodium chloride, but looking down, we see some of these very small peaks that are present as well. So we can actually identify there's a calcium sulfate present in this particular sample as well. And in this case, it actually makes sense because calcium sulfate is an anti-caking agent for salt to stop it from actually clumping together. So we can detect these sorts of very small minor phases present as well. The instrument that we have is a Bruker D8 Advanced XRD. This is a powder X-ray diffractometer. We operate with a copper X-ray source. We have a one-dimensional Lynx-Eye XE detector. And as I said, we are operating in a Bragg-Brentano geometry or a theta to theta geometry here. And we can go from about 3 to 120 degrees, 2 theta on this goniometer. Again, this instrument, much like the XRF, is really for high throughput. It is an efficient and lean instrument. So we have a sample auto changer here that can, again, pick up your samples, load them into the instrument, run them, put them back and pick up the next sample. And we have 2 user towers are available. Each can hold 15 samples. So you could conceivably mount 30 samples in this instrument, program them all, let it run over the weekend, and then come back the following week and pick up all of your samples and all of your data. So when you are using these instruments, either of them, really try to leverage the high throughput nature of these techniques. That is really what they are there for. The types of samples that we can put into these, so we have a few different holders here to work with different materials. The most common holder that we have here is the standard powder diffractometer holder. So this is for finely ground powder materials compacted into a small flat disc in the middle of either the metal or the polymer holders here. We can work with large solid samples as well, whether this be solid film-like materials. It could be a piece of glass with a deposited film on it. It could be polished cross-sections of alloys, minerals, materials, polymers, things like that. It just needs to fit inside of this diameter here. So about 38 millimeters, 35 millimeters by about 4 to 5 millimeters thickness is the maximum that you can get into one of these holders. But they are for large solid samples. We also have zero background holders for very small amounts of material. So if you have milligrams of material to work with, that's what these holders are for. So we make a small smear in the middle here and then run them on the zero background holders. And then we have backloading specimen holders as well for doing some quantitative analysis as well. So another piece of flexible sample mounting there as well. Similar to the XRF, we have the data analysis techniques that you need. This is a different piece of software called DIFFRAC.EVA. We have EVA version 6 at the moment is what we're operating with. Now, nicely, the EVA software we can actually give you an installer for, and you can install this on your own UOM-owned PC as well. We can give you the installer for the open database, the COD crystallography open database, to allow you to do your own phase identification. Otherwise, we have the larger paid ICDD database available on the XRD PC as well for you to use while you're operating the instrument, or you can book it out for data analysis as well. It allows you to do basic evaluation, phase identification, semi-quantification, peak analysis. You can pull out your crystallite size. So this, for example, is that salt again, looking at this particular peak here, using this particular evaluation mode. You can pull out the crystallite size, for example. So that's all in DIFFRAC.EVA. Estimate the crystallinity of your material and a lot more. The software is very, very powerful as well. So EVA 6 is what we have for the routine data analysis available for you to use. And as I sort of touched on right at the start, sample preparation for both of these techniques is critical. You really do need to think about how you're presenting your samples to the instruments to ensure you get something that's meaningful out of them. We have a lot of capability to help you with this as well in the lab space. So we have, for example, and a majority of this is really geared towards XRF, but it does apply to XRD as well. We have, for example, our XRD mill macrone micronizer. So this allows you to mill your samples down from starting at about, say, 500 micron particle size down to about 10 micron particle size. So this allows you to make very, very fine powders. This is generally one of the first steps towards creating XRF pellets, for example. So we mix these fine powders with a binder material, put them into a die, and then press them with 25 tons with our pellet press here to create nice pressed pellets for XRF. Working with liquids or powders in the XRF, we have the films that you need. So we have two different films, polypropylene and mylar, for different types of materials. We've got plenty of sample cups as well. So we have most of what you need to get your sample preparation right for both XRD and XRF. And when it comes to your samples and actually being trained on these instruments, we will talk to you specifically about your samples and the best way to approach this, because this is a very broad field to understand how to deal with everyone's specific samples. But just to give you a bit of a feeling for what you need for these techniques, for powder XRD, if you're working with powders that are already finely ground, we need about a 1.5 milliliter or 1.5 cubic centimeter centrifuge tube worth of material. So one of these little 1.5 mil tubes full of powder material is about the right amount of material that you need to do powder XRD in a standard holder. Ideally, you want the particle size to be less than 50 microns as well. Kind of the consistency of talcum powder is really the rule of thumb there. For XRF, if we assume we're going to be working with pressed pellets, we want about 5 cubic centimeters worth of material to make a pellet. And that would be a similar amount of material if we're going to put them directly into one of these sample cups and have the thickness thick enough to get fluorescence from the bulk of the material as well. And as much as possible, you want these materials to be homogeneous so that you're getting fluorescence from there's not different domains within your material where you have more concentration over some other areas. You want them to be really homogeneous to give you as accurate a representation as is possible. Okay, just before we wrap things up, the final thing I wanted to touch on is a question I get asked quite a lot, which is, which should I use, XRF or EDX, when I'm looking at my samples? So I just wanted to highlight the two techniques here right at the end before we wrap up, to really compare the two with you. So I've given you an introduction about the XRF already. If we talk about EDX, the actual physics of what's going on is basically the same sort of thing. We are talking about X-ray fluorescence from the atoms in your sample as well. However, the difference with EDX is that our probe is now an electron beam. So it's the electrons that are doing the initial core shell, the core level ionization of your atoms in particular. What this means is the surface sensitivity of EDX tends to be greater. So you're dealing with, say, 1 to 3 to 5 microns worth of information depth in EDX, as opposed to potentially up to millimeters of information depth with XRF. The other big difference between these two techniques or these two instruments specifically, are PUMA and the FlexSem that we have on the MCFP, is that this is effectively a bulk general compositional analysis. So you're looking at a very large area and you're not looking at any specific domains within your sample to get composition from that area. With EDX, that's very different. You are using your electron beam, you're defining exactly where you want to capture your data from. So EDX is going to give you more of that spatial information if you have different domains within your sample and you want to identify the elements that are present in those different domains. Finally, EDX is much more sensitive to the light elements compared to the heavy elements. XRF, better with the heavy elements than the light elements. So again, there's a bit of a contrast there. And then the last thing, EDX, of course, or SEM in general, you can't work with liquid samples. It is a vacuum technique. So if you want composition of a liquid sample, XRF is your only option between these two samples. EDX is just not going to work in that particular case. But if you're not sure about the best way to do it, reach out to us and ask the question, this is my sample, this is what I have, what's the best technique to apply to get this particular answer? And we're very happy to help you if we can. And so that's everything I wanted to go through with you today. That was an overview of X-ray characterization at the MCFP. And so I'll now open it up for anyone to ask any questions that they may like, and we can sit here for 10, 15, 20 minutes and just have a bit of a chat about the capability. So feel free to unmute yourselves if you'd like to ask the question, otherwise throw them into the chat box and I'll answer them from there as well. And thank you very much for joining us.